I'm going to talk on autonomous cyber, and this is very much a strategic talk. Now, I was told when I push this green button it would advance, and it doesn't.
It does become
Ah. Oh, it's just slow on here. Okay. I'm going to talk about three things in this talk. I'm going to talk about reliance, I'm going to talk about contest, and I'm then going to talk about artificial intelligence. I'll start with reliance, and this is really about the reliance of society on information environments. So moving from the industrial age to the information age, I'll illustrate in a defence context, and it's because the information revolution has transformed warfare. So World War II represents industrial age warfare, where people interact directly with their industrial machines to fight the war. And I've got an image there of a dapper looking pilot and his Spitfire aircraft to illustrate that. Modern warfare is completely different to that. It looks like the image I have on the right. It's characterised by information age warfare, where people now interface to an information environment that in turn interfaces to their industrial machines. And in fact, with a joint strike fighter, you don't let the pilot control anything, because if you did, the plane would crash. So what we see here is warfare has moved from a two-tier system to a three-tier system. This information revolution has had this effect not just on warfare, but on society more generally. And the physical and human environments in society now have a total reliance on the information environments that separate them. To illustrate that, at the physical environment level, we're sensing almost everything in the physical world digitally. We'll have a trillion sensors in the world in the early 2020s. On the human side, we're describing almost everything about humanity digitally. Of the 7.6 billion people in the world, there are over 2 billion Facebook users and over 1 billion WeChat users. And we're distributing almost everything digitally, connecting all of our physical and virtual devices into the Internet of Things. So we're constructing a digital representation of the world and making it accessible to anyone, anywhere. And this has created reliance. So our physical industrial world is now totally reliant on information environments. And this includes all of society's critical infrastructure. So our power and water, our telecommunications, our industries. I've illustrated here with agriculture, but it applies to all of them, including banking. Our hospitals, our transportation, and our security, they're all reliant on information environments to function. So people no longer directly control the physical industrial world. People instead issue commands to an information environment, and that information environment directly controls the physical industrial world. And the consequence of that is, if you control the information environments, then you can control the physical industrial world. All right, what about the human side of this? This comes down to a question of truth. And I'll start by asking, well, what is truth? If you study philosophy, there are two dominant theories of truth. I'll quickly outline what they are with a simple example of the cat is on the mat. So the first is what's called the correspondence theory of truth. It says the statement is true if it corresponds with the world. So in this case, do we have a cat? Yes, we do. Do we have a mat? Yes, we do. Is the cat on the mat? Yes, it is. Therefore, that statement is true because it corresponds with the way the world is. The other theory of truth is the coherence theory of truth, and this says the statement is true if it coheres with typically trusted people's beliefs. So this is a bit like phone a friend, and you say to your 3 trusted advisors, well, do you think the cat's on the mat? They all come back and say yes, and so you accept that it's true. The really critical point about that is for both of these theories of truth, they're now decided through screens. And so for the correspondence theory of truth, you tend not to look out the window anymore. You tend to look at your screen to see what's going on in the world. And the example I've got here is Moscow weather through EarthCam. And for coherence theory of truth, it tends not to be phone a friend anymore. It tends to be social media through Facebook and Twitter. And the really important thing about that is through this reliance, you have the correspondence theory of truth, assigning truth based on correspondence with the world. But this now comes through digital images, and those digital images can be manipulated by image and video editors. And with the coherence theory of truth, that's based on the coherence of opinion, but this now comes through social media that can be manipulated through fake news. And so we now have the situation where if you control the information environments, then you can control people's truth. What about the information layer that sits between these two? So this takes us into the territory of algorithmic warfare, where you're attacking and defending algorithms in the information environment. Key point here is there's a tendency to only focus on flaws in the coding of algorithms and believe that algorithm warfare threats are eliminated once the code is appropriately patched. And this is not true. The reason it's not true is because there are features in those algorithms, and those features can be exploited, even in perfectly coded algorithms. Simple example, this is an example from the literature. So since 2011, machine learning image recognition algorithms have significantly outperformed people, but perfect machine learning algorithms are also subject to algorithmic warfare. And here's the example. So you have a school bus, which the machine correctly classified as a school bus. You do some stretch perturbations by playing with the data, and you get a school bus, which looks like a school bus to us, but the machine then misclassifies it as an ostrich. And I have a group of people in my division that are expert at doing this to machine learning algorithms. So the power of the information lies in its algorithms. Flawed algorithms provide vulnerabilities that can be exploited until patched, but perfect algorithms are also vulnerable because they have features that can be exploited. And so if you control the information environments through its algorithms, then you can control the information. Now, if you sum these three things together that I've just been talking about, if you control the information environments, then you can control the physical industrial world. If you control the information environments, then you can control people's truth. And if you control the information environments through the algorithms, then you can control the information. Bottom line, if you control the information environments, you have control. That then brings us to the second part of the talk, which is about contest, and this is about fighting the war from inside the information environments. So I just said if you control the information environments, then you have control. So here's our society with those elements that I've just talked about. And imagine we now have an information contest happening on those things. So at the physical level, suppose an adversary takes out our physical capabilities. So you now have no power, no telecommunications, no industry, no hospitals, no transportation, no commerce, no security. They're all gone. If the attack was also at the human level, it takes away your access to the external world and your understanding of what's going on by accessing the external world. It also takes away your understanding through social media. And in a way, worse still, instead of just taking those things out, it could be practicing deception within any of those things that I've just been talking about. The outcome of all this is you go from society to no society. And if you think of COVID, that's a cakewalk compared to the scenario that I'm talking about here. This has been realised by people, and so in June of 19, the UK Chief of Army said the following: the weaponisation of data, ideas and goods by adversaries such as Russia, he picked out Russia, poses a particular risk, a bigger risk, than missiles and tanks. The emergence of these disruptive technologies is so prevalent and rapid that what we need now is an urgent reappraisal of how, with what, and by whom war is waged in the future. So this brings us to information warfare, which is a kind of more general issue than just thinking about cyber warfare. And this diagram that I have here illustrates it. So I've talked about the three-tier environments where you've got human information and physical, with the information typically separating the human and the physical. And you're now going to launch an attack from the red side onto the blue side. And you'll typically do that from within the information environments. And there's three things you can target on the blue side. You can target their physical environments, which is what electronic warfare is about. You can target their information environments, which is what cyber warfare is about. And you can attack the humans through things like social media, etc., which is what influence operations are about. And it's really the collective of these three things that constitutes information warfare, as I've described it with my little summation at the top of the slide. So I did a talk about 18 months ago at the National Press Club on this sort of stuff, and I put up this slide, which I called Lambert's Information Warfare Maturity Model. And it kind of goes like this. If you look at the way things have progressed, you pick a company or something and they want to develop some capability to provide a function, then they'll typically go through a design phase and they'll do some sort of implementation phase, and then they've got their product to deliver the function. The trouble with that is typically something goes wrong, you'll have function errors, and so you need to do a process that's a bit better than that. So where everyone then moves to is to verification. And so now you're developing a capability to provide a safe and reliable function. And to do that, you'll typically introduce some sort of proof capability or some sort of testing capability. And for the great bulk of Australian industry, that's where they sit. They think they have finished their task when they have built some capability that provides safe and reliable function. That used to be true, but the trouble now is it's not a benign environment and your function might be attacked by people. So we now move to a third phase, and the third phase starts to worry about security. You develop capability to provide safe, secure, and reliable function now. And typically that security is done by building some kind of wall around what you're trying to do or what you're trying to protect, and you're trying to protect it from somebody attacking or penetrating it. This is symptomatic of the cyber industry, which is progressing beyond where most of Australian industry is at the moment. And the trouble with that is somebody is going to breach your wall. Sooner or later, somebody's going to get through, and then there's the question of what are you going to do about it when they do. So cybersecurity needs computer support to find malicious needles in normal haystacks. Cybersecurity needs computer support to handle the speed of cyber operations, and cybersecurity is facing a large personnel deficit, as we heard earlier this morning. So there's a strong need for AI to come in and assist with cybersecurity because of those three reasons. And we already have some of this going on now. We already have machines that automatically patch vulnerabilities in our own operating systems. And if you work in an organization like mine, you have ones that craft exploits to engage with other systems, I'll say. So what that means is the contest is moving inside the information environments. So what does that look like? Well, there was a philosopher in 1949 called Gilbert Ryle who coined the phrase ghost in the machine. He was actually making reference to Descartes' mind-body theory from the mid-1600s. But if you think about what's going on now, that's what we've actually got starting to happen. So we've got AI digital ghosts as AI software and firmware operating on hardware that have actually now become the ghosts in the machine. And so the future starts to look a bit like this picture I've got here. You've got AI digital ghosts fighting the war from inside the information environment. So you've got a red AI and a blue AI inside the information environment. And they're playing that game, that information warfare game, where they're targeting the human and the information and the physical environments of their opponent. So that brings us to a fourth stage, which is a future industry stage, because it's not really out there. So this is me crystal balling, if you like. And I think the next stage is going to be these AI digital ghosts, where you're developing capability that can contest to provide safe, secure, and reliable functions. So once someone penetrates inside your castle wall, these things go to work to try and defend and protect what you have. So what are they going to have to be able to do? They're going to have to be able to contest, which means they need to be able to protect and defend and attack. And I've used a medieval knight's constructs to illustrate those three elements. And they're also going to have awareness, really good awareness of their environment. So they're going to have to be able to sense, they're going to have to be able to analyze, and they're going to have to be able to shape their environment as well. So is that the end of the game? No, it's not the end of the game either, because you don't want a bunch of these AI digital ghosts all running around doing their own thing inside your system. You're going to have to do some sort of coordination. You don't want isolated intents. So then there's a fifth stage, which is what here I've called the AI digital force. And that's about developing a coordinated capability that can contest and provide safe, secure, and reliable function. So that's going to need command and control constructs, and that's going to need communication constructs across these agents. And one way to think of this is a bit like digital soldiers in digital armies operating inside information environments. So this is putting a bit of a load on AI. Does AI actually have the capacity to deliver all this? And the short answer is not yet. And I'll try and explain why that is so. To do that, I'll give you a quick history of AI in one slide, where I can't talk about all the bits in here, or I'd be here all day. So AI started in 1956 at Dartmouth College, and the very first phase was the search phase of AI. Each of these balloons corresponds to a theme that underpinned the way people thought at the time. The one to focus on here is the purple one at the end that says general purpose search. The original idea was general purpose search was the basis of all intelligence. That turned out not to be the case, and they realised they needed specific knowledge. That then led to the second phase, the representation phase of AI. And again, if you focus on the purple balloon, this was about representing knowledge, because they realised that they need to work out how to represent knowledge inside the machine in order to do things. They did that, they worked out various representation schemes, but then they still needed the knowledge. That led to the next phase, which was the knowledge phase. And here's where you started having things like expert systems, which you'll see in the red balloon over on the far left. And in the purple, you can see there, it was all about knowledge acquisition and domain knowledge representation. You had two other contenders come and start playing at that time. One is what's sometimes referred to as situated AI, where you had a focus on embeddedness. So you had things like Rodney Brooks's insect robots, for those of you who are familiar with that. And the other one that surfaced at the time was the connectionist model. So this is where you started having your neural networks with the early forms of it, with the first back propagation and the like. We then went to the agent phase. The key point there was the social agents was a way of handling scale, because all three of those elements of the knowledge phase failed to handle scale. Social agents broke the problem up. And then in the next phase, which is the phase we're in now, is the learning phase, which is where the big data and deep learning took off. And that was really an extension of the connectionist approach. And that still has a problem with things like explanation and trust. To cut a long story short, none of those systems are actually suitable for handling the problem that we've got. And the reason is something that John Searle promoted in 1980, and that is the machine merely manipulates symbols and numbers, and it doesn't actually understand what those symbols and numbers are about. And it needs humans hanging off the edge of them to do that for us. So in order to do this kind of thing that we're talking about here, I think we need an additional phase to be added to AI. We need a semantic phase, which will introduce some of those capabilities. So in conclusion, oh, that was slow. First, society is totally reliant on the information environment. Second, the future will involve AI digital ghosts fighting the war from inside contested information environments. And finally, a semantic phase of AI is needed to deliver these AI digital ghosts. And that's me done. Thank you very much.
Thanks a lot for such an enlightening talk. I will now take the questions. Yes, Lois.
Thanks, Dale. That was great. You mentioned humans only at the end of that talk. Where are the humans in Lambert's model, and what training do those humans need to be trained in?
Yeah, quite a lot. I actually mentioned humans all the way through because I had a human environment, if you recall. Yeah. No, I get your point, Lewis. There's been a transition going on in defence where there used to be a lot of discussion about humans in the loop, and then it moved to humans on the loop, and now there's a lot of discussion about humans out of the loop, and the reason for that is the speed. To give you an example, in the bio, they talked about a solution that I built for Sweden many years ago. That had to make decisions in less than 2 milliseconds sometimes, and it could handle about 450 easily aircraft flying around Europe and monitoring them and understanding what they're doing. How many can a human handle? I was at a talk in Florence in 2006 where people investigated this, and the answer was 6.8. So there's this huge difference. One of the challenges that comes with the semantics is to introduce those human type concepts into the system, because you don't want the humans completely divorced, and you also don't want the situation where the AI does a whole bunch of things and gets to a problem and goes, I don't know what to do now, over to you human, where the human's been completely out of the context up until that point. That's just a disaster as well. The other bit I'll throw in here without talking too much is ethics. And I think we have to build ethics inside the machines as well, because of the speed and the amount of activity that will be happening inside the machines independently of the humans. There's lots of forks there.
Thank you. Any more questions? Yes, Trent.
Thanks, Dale. The explosion we've seen in the phase that's just gone with the deep learning revolutions being driven by massive amounts of data.
Yep.
What do you see is that the tipping point for getting into the next phase?
It's surfacing now. So you can start to see an interesting thing to read is Hinton, Bengio, LeCun got the Turing Award, and there was an interview with them by Kaubling, and which you can find on the internet, and it's quite interesting because they start talking about the things they can't do at the moment as well. And so there's problems with abstraction, there's problems with explanation and trust, and the only way you're going to resolve these problems, I think, is by, and this goes back to an old debate between Descartes and Locke, 1600s. I think you're going to have to embed some of that conceptualization in the machine a priori, particularly the meanings of things, and then let your machine learning run on those, rather than trying to expect your machine to understand concepts like democracy from scratch, right? Good luck. So I think that balance, you're going to have to balance those two things.